Here I am going to discuss a problem of electrostatics in which we have to find force on a dipole placed near a uniformly charged long thread. And there are three orientations of dipole, and in each case we have to find the force of the dipole. In first case, the dipole is placed along the thread, that means parallel to thread. So, and it is placed at a distance basically r. It is located at a distance r from thread. In any case, it is a distance r in all the cases from the thread. In first case, it is along the thread. That means P vector is parallel to thread. In this case, force is very easy to find, and the answer is 0 because the dipole has two charges, and on each charge we will have same electric field, because due to long thread we know that field is lambda upon 2 pi epsilon naught r along this radius. To here, both are experiencing basically uniform field, and uniform field dipole experience 0 force that can be easily realized. This will experience force Q into E in this direction, and same is here, so negative charge force will be here QE, so it will not experience any force, but obviously it will experience a torque, but we don't have to find it. If it is to be found, then we can apply that relation P cross E. The P and E are at 90 degrees, easily it can be found. In second case, the dipole is along radius vector, that this radius vector and dipole is parallel to it. This is the fit case where we can apply this relation. A very popular relation for finding force on dipole is P dy dr if dipole is oriented along r. Then this formula gives proper result. So we don't have to apply much any calculation, just use this formula. E is given by this relation, and dy dr will be lambda upon 2 pi epsilon naught r square, just simply multiply by P. As far as direction is concerned, though here we are getting negatives, we can interpret the force is going to be towards the thread, but sometime the sign may lead to confusion whether to feel it separately. Here field is more, negative charge will experience force towards the thread and larger force because field is larger. Positive charge is away from thread, so it will experience force in right because field is in the right and charge is positive, but field is lesser here, so this force is lesser, this is larger, so there will be net attraction. So this will be the force towards the thread. Now third case is a tough case, and here basically we have to find the force when dipole is placed at right angle to the thread and the radius vector. So dipole is perpendicular to this radius also and to thread also. So we can say if thread is along z axis and radius vector is along x axis, then dipole is along y axis. So better in this case try to observe thread from z axis from the top. From top I am observing it is oriented along z axis. This is say x axis in which distance is r, and dipole is placed along y axis like this. So in this case what we will do, we will try to find force on individual poles, and by symmetry field on both poles will be of same magnitude, and this dipole will experience field radially like this pole, and this pole will experience field like this in both cases radially outward. But since this is negative charge, here force will be opposite to field, so it will be towards that thread. Here it will be away from threads in the same direction as the field. And by symmetry, both will experience same numerical value of force. Field here will be lambda upon 2 pi epsilon naught r. R should be this length, but since dipole is of a small size, this r and this r can be taken as same. Now, how to find now net field? So this force is 10 unit, this is 10 unit. Then their horizontal component, their components along x-axis will be cancelled, mutually cancelled by symmetry. The resultant will be along y only, and that will be, if we see this angle is theta, here I have some more clearly, this force and this force, their x component will be parallel, given by cos component, and the y component will contain sin theta. So this force into sin theta and this force into sin theta both will be added. We will get this resultant force, simplify and place the value of sin theta from this diagram. Sin theta will be nearly same as tan theta, because theta is going to be small, because dipole size is small. And this will be L by 2 upon R, right? So place sin theta as L by 2 upon R here. You will get net force L by 2 में 2 कट जाएगा, R यहाँ नीचे आके that will be R square, right? So net force will be lambda p upon 2 pi epsilon R square. Same expression is here, but here direction is attractive. Here force is 0. Here direction will be interesting. It will be parallel to p vector. You can realize this will have upward component. This is also upward component. So in this case, dipole will experience a force parallel to its own p vector, right? We can discuss one more problem for force on dipole that is interesting. We have a ring, uniformly charged ring, and we know that ring on its axis produces this much field. A question may be asked that if we have a dipole and we placed on the axis, will there be a point where dipole experiences zero force? The answer is yes, because we know here graph of field is like this, something like this. We have a maxima, and at maxima dy dx will be 0, and this is a expression of force on dipole as we have discussed earlier. So at maxima dy dx is 0, and that point we already know, it is very popular result, x equal to r by root 2. So here if we place dipole along the axis, it will experience 0 force. And another question may be asked, if we place the dipole along the axis but at center of the ring, what will be force? The field is 0. Somebody may claim that since field is 0 here, force will be 0. That is wrong. Force on dipole is not proportional to field, it is proportional to gradient of field, right? So at center, x is very small. So let us first simplify this expression so that we can easily differentiate it. Near center, this expression will be qx upon 4 pi epsilon naught 1 by r cube. This is E, close to center. So dy dx, if we calculate dy dx, this will be removed. We will get dy dx as q upon 4 pi epsilon naught 1 by r cube. कहाँ पर at x equal to 0, and then just multiply by p. So the force will be p q upon 4 pi epsilon naught r cube, and this force will be obviously parallel to p axis, p vector. And individually if we see here, field is like this, so this positive pole will feel force towards right, and in the left of center negative charge is there. Field is in the left direction, but force will be in the right direction, so both forces will be added, right? So we will get net finite force parallel to p vector, right? This is also a very interesting problem, and this may be asked in the advance.